So I'm Ethan Katz-Bassett from the University of Washington, and I'm going to be talking about our system to measure the reverse path back to you from an arbitrary destination without requiring control of the destination. This is work with collaborators at University of Washington, University of California, San Diego, and University of Minnesota. Traceroute's the most used internet diagnostic tool today. People use it to check if a destination's reachable. If the destination is reachable, you can see what path's taken. If it's not reachable, you can try to look at where the path seems to be broken. You can use Traceroute to troubleshoot problems. If a path seems to be higher latency, you can see if the path's longer than necessary. Maybe there's an out-of-date local pref. At University of Washington, we use it for a number of things. We map the internet. We have a system that predicts performance and compares ISP performance. And I was at RIPE last year in Berlin talking about my system Hubble that detects reachability problems in black holes across the internet using traceroutes. So what I quickly realized with Hubble was that a limitation of Traceroute was really restricting my ability to tell what was going on. So if we consider the communication between me in the top left and a web server down at the bottom, there's some path that traffic takes from my computer to the web server. In this case, it's the purple path. And then there's some path that traffic takes from the web server back to me, in this case, the red path. And generally, paths on the internet are asymmetric, so the paths will be different in some way. Traceroute's a great tool to measure the path from you to anywhere. And the key phrase there is that Traceroute just measures the path from you. So here it can measure the purple path. But it doesn't give me a way to measure the red path. In order to do that, I would actually need to run Traceroute from the web server. So with Hubble, this meant that if the problem was on the forward path, I could get a pretty good idea of what was going on. But I was basically flying blind if the problem was on the reverse path. I'm really only getting part of the story, and that was limiting my work. And similarly, it seems to limit what we can do operationally. So I was at NANOG in January, and there was a tutorial on troubleshooting problems. And I have a quote from it up there. The #1 go-to tool is Traceroute. The #1 plague of Traceroute is path asymmetry. And that's because the reverse path itself is completely invisible. Some of my colleagues at University of Washington are working with a large content provider to try to troubleshoot performance problems that some of the clients of that content provider are having. So they found that 20% of the clients were experiencing severely inflated latencies, even though there was a server nearby. For example, some clients in Taiwan were experiencing really poor latencies of over 500 milliseconds, even though they were being redirected to a data center in Southeast Asia. So they suspected that the problem was a circuitous reverse path, but they really have almost no visibility into the reverse path. And I have their conclusion up there from a paper that they're working on. In order to more precisely troubleshoot problems, they need the ability to gather information about the reverse path back from clients to their nodes. So we're left with wanting the reverse path information in multiple instances. And in fact, I think it's useful in many of the cases when we're currently using Traceroute. But in order to get it, we actually have to run Traceroute from the destination we care about. So generally, we don't control those destinations. There's a couple things that we can do. We can use public Traceroute servers, but there's only a couple hundred of those around the world. So that's only going to work if there happens to be one in the destination that you care about. Maybe we can mail a mailing list and ask for help, but obviously that's not a very, very scalable approach. We can assume symmetric routing, and I think that's what we end up falling back on. But most paths on the internet are asymmetric. So none of these really work as well or as often as we'd like, and we end up using them because we have to, not because we want to. The goal of this work is a reverse traceroute that works without control of the destination. We can't just use TTL limiting like with Traceroute because the destination is actually going to set the TTL value to a normal value. And anyway, even if there was a TTL expired message along the path, that error would go to the destination, and we don't control the destination, so we wouldn't see it. So instead of using TTL, we're going to use IP options to measure the reverse hops. IP options are generally reflected in the reply, so they're going to work over both the forward and the reverse path. The first option that we're going to use is the record route option. Record route will record the first 9 routers along the path, and so if the destination is within 8, then all the remaining slots will be filled out on the reverse path. So this is great if we're within 8, but the average internet path is about 15 hops in both directions, 30 round trips, so this is only going to work if we happen to be near the destination that we care about. The second option that we're going to use is the timestamp option. Timestamps lets us specify up to 4 IP addresses, and they're ordered, and each will record its timestamp if it's traversed in order. So the key is that the timestamp checks for the routers in order. So a router is only going to stamp if it's the address in the next open slot, not if it appears further on. So that means that if we ask for the destination's timestamp, then any stamp after that will have to have been on the reverse path. So in particular, what we can do is if we want to figure out if a router is on the reverse path back from D, we can ping D, and we can ask for D's timestamp and the router R's timestamp. If we see a timestamp from R, we know it's on the reverse path. What this lets us do is use existing internet maps to see what adjacent possibilities might be on the reverse path, and then we can use timestamp to check which one actually is. The problem here is that timestamp is filtered all over the place, and it's very limited deployment. So this ends up being great if we happen to be near enough to use record route, or if we're interested in a destination that supports timestamp. And in a few slides, I'll get into how often we see those supported. We now have a couple techniques that can sometimes measure reverse hops. But record route's only useful if we're measuring from close to the destination. So what we're going to do is use distributed vantage points and source address spoofing in order to extend the coverage of that. So in this picture, you see my computer up there. I'm trying to measure the reverse path from the web server back to my computer, and I have another computer that I control down in the bottom. Source address spoofing is going to let us use any vantage point that's within 8 hops, regardless of whether or not it's the source that we want to measure. So let's say that that other computer is within 8 hops. What we're going to do is have it ping the web server with record route enabled, but it'll spoof the address and say that it's coming from me. The packet will get to the web server. It'll think it came from me, and so it will reply back to me along the red path, and so we'll be able to measure the red path without having to probe the forward path towards the web server. So we can now measure a reverse hop back from anywhere as long as we have some vantage point near the destination. So okay, I just said we're going to use spoofing. We're well aware of the security issues with this, but we think that it's feasible to employ it as a useful measurement tool with limits on it that are going to keep it from being dangerous. What we envision is using a restricted version just on measurement testbeds, and we'll have a list of who we're able to spoof as, so we're only going to ever spoof as nodes that we can control. That means we're always going to be accountable for the packets that we send. We're basically using the spoofing as a reply to address, getting the reply to go to a different one of our vantage points. We're also going to use rate limits and restrict the destinations that we probe. So between the rate limiting and only spoofing as other nodes that we can control, this really has little in common with the nefarious uses of spoofing that use it for concealment. It's sort of more like the address rewriting that NATs might use when we're trying to control the traffic flow to a cooperative node that we have. So we've sent millions of spoof probes so far to at least tens of thousands, maybe hundreds of thousands of destinations at this point. We've received no complaints. A small number of spoofing vantage points are able to support our entire system. So for the rest of the talk, I'm going to use around 30. So really, you can filter all other locations and just give us a few ports at a few sites, and that's enough to support the system. As I said before, we're using IP options, and options are generally sent to the route processor. So some networks filter or ignore them in order to reduce the burden and maybe reduce the potential for abuse. So we looked at how much support we actually see of options. So Planet Lab is a testbed with hundreds of computers around the world, and we use that to assess it. We issued trace routes from Planet Lab to all prefixes, gathered the set of IP addresses, and saw how many of them supported the options. So we found that 58% of the IP addresses that we observed were within 8 hops of some Planet Lab node. This means that more than half of them are close enough for us to measure from some vantage point using record route and get a reverse hop. Last year, Rob Sherwood presented a study at SIGCOMM where he looked at record route support. He found that about 1% of the routers observable from Planet Lab dropped record route packets, and about 9% don't record but don't drop the packet. They'll pass it on without recording. We also looked at coverage of timestamps. So we found that about 37% of IP addresses gave valid timestamps. An additional 18% replied, but with a timestamp of 0. So not useful in our case, but they also aren't dropping or filtering the packet. We looked at the top 100 ASs in terms of the most distinct IP addresses that we saw and found that 61 of them gave timestamps, valid timestamps for most of the routers. The rest are either dropping the packets, ignoring the option, or maybe they're getting filtered along the path. So overall, we saw that most big ASs seem to have at least some supportive options. Neither record route nor timestamp is a complete solution, but the combination with spoofing ends up being pretty powerful. So now we have a way using IP options to measure a hop back from the destination. We need a way to make a path out of that. And what we're going to do is build the path incrementally by exploiting the fact that most routing on the internet is destination-based. This means that once we get to a certain path on a certain hop along the path, the next hop tends to depend only on the destination, not on the source or the path so far. So if we know the reverse path from some destination D goes through router R, we need to only determine the path from R back to S to get the complete path. We can stitch it together. This assumption doesn't always hold, but it holds often enough for us to base the system around it. I'm going to go through an example now of how this works. So here we have a source S. We're trying to measure the reverse path from the destination D back to S, and I have a set of vantage points, V1, V2, and V3 around the world that I can use. Some of them can spoof. The first thing I'm going to do is just issue standard trace routes from all of the vantage points to the source. This is going to give me an atlas of paths that I know to the source. If I intersect one of these paths, I'm going to assume that the path that I care about follows it back. Next, I'm going to find some vantage point that's within 8 hops of the destination so it can use record route. In this case, let's say that V3 is. V3 will then send a record route ping to the destination, but spoof and claim that it's coming from S. So when that packet gets to D, some number of the hops will be filled out, let's say 7. D will add itself in and then reply to S. So when the response gets back to S, there's now reverse path information in it. We know that R1's on the reverse path, and it looks something like this. We can now repeat that process. We'll assume destination-based routing, so we just have to get the path back from R1. And let's say that V2 is within 8 hops of R1. We'll send a record route, spoof record route from V2. And this time when it gets back to S, let's say we found 2 new hops, R2 and R3. Path looks like this. Now let's say that none of our vantage points is within 8 hops of R3, so we can't use record route. This is when we'll use timestamp. We're going to look at an established map of the internet, so there's a number of mapping services out there, and we just use one of them. And we'll look at all the routers that are adjacent to R3. These are the possibilities for the next hop. So let's say R4 and R5 are. We'll then test them one at a time to see which one's on the reverse path. So we're going to send a timestamp ping from the source to R3, and we'll ask for R3 and then R4 as timestamp. So that forces if we see R4 as timestamp, that means it was on the reverse path because R3 had to stamp first. Send it to R3, R3 stamps. We get the response back. There is a stamp for R4, so we now know that R4 is on that reverse path. So it looks like this. At this point, we've intersected a known path, and so we're going to assume with destination-based routing that it's going to follow V1's blue path into S. Looks like this. So the techniques combine together to let us build up this path incrementally. So I've given you the technique now, and we can look at how often it works. To do this, I chose 200 random destinations around the internet, and I used those as the destinations. The sources were 11 Planet Lab sites scattered around the world. If in a particular case we're unable to get a complete path, what we'll do is issue a standard trace route from the source to the destination. We'll assume that the last hop is symmetric, and then we'll try to use our reverse traceroute technique to measure the rest of the way. If that doesn't work, we'll assume the last 2 are symmetric, and so on until we can get a complete path the rest of the way. So the metric captured in this graph is the number of hops that we have to assume are symmetric in order to calculate the complete reverse path. So on the x-axis, we have that, the number of hops that we assume are symmetric. It's a CDF, so the y-axis is the cumulative fraction of source-destination pairs. And the easiest way to explain it is just to point out the highlighted points that I have there. So we see that in just over 40% of the cases, it's the purple point there, we have a value of 0, which means we didn't have to assume any symmetry. We were able to measure a complete reverse path. In the median, we have the blue point. We have to assume the first hop was symmetric, and we were able to measure a reverse path the rest of the way back. I've just shown that we can often measure a reverse path. We'd also like it to be accurate. And one measure of accuracy is whether it's going to give you the same thing that you would see if you actually had control of the destination and measured a trace route directly. So we're going to use that as our metric. We lack ground truth for the paths on the internet as a whole. What we're going to do is use Planet Lab as destinations this time. And when we use Planet Lab, for the reverse trace route, we'll assume that we don't control the destination and just use the techniques that I presented in this talk. And then we'll compare that to a direct trace route when we actually do control the destination and can directly issue the trace route. So in terms of how often the technique worked, it was almost identical to the previous data set. And what I'm capturing on this graph is how similar are those 2 paths, the one where we do use the destination and issue a trace route directly to one when we don't use the destination and use our reverse trace route technique. So on the x-axis, we have the fraction of hops along the directly measured trace route that we also saw on our reverse trace route. This particular graph is a CCDF. So to explain it, I'll just point out a couple points. The black line is how well you will do if you just assume the path is symmetric. And in the median case there, we see that you get 38% of the hops right. The red line is our technique. And in the median case there, we see 87% of the same hops that you would see if you issued a direct traceroute. One problem is that it's hard to know if two hops are actually the same when we're trying to compare paths. So we know we're doing pretty well. It's not clear why there's the gap. The reason it's hard to tell if two hops are the same is because Traceroute will generally give you the incoming interface on a router, whereas RecordRoute will often give you the outgoing one or sometimes the loopback. So it's hard to know which ones actually belong on the same router. We borrowed existing techniques to try to identify which interfaces are on the same router, but they don't always work. So some of the gap between the red line and an ideal value, which would just be 1, might just be because we don't know hops are the same. To look at that, in addition to looking at if we were getting the same router, we also looked at whether we were able to tell you the same pops that you would see with Traceroute. And here by a pop, I just mean a given AS in a given city, and we just identify pops based on the DNS names. So the blue line captures how well we're doing in terms of pop similarity. And there, we see that in the median case, we're able to identify 100% all of the pops that you would see on a directly measured traceroute. So it seems that a bunch of the gap there is just that we don't know which routers are the same. It's also possible that traceroute and reverse traceroute both see correct paths, but they see different correct paths. And that could either be because they're getting load balanced differently, or there could have been a path change in between when I made the two measurements. So I looked at that by issuing traceroutes one day and then issuing traceroutes again the next day and seeing how many changed. And that granularity of a day was about the same granularity between the reverse traceroute measurements and the traceroute measurements. And from one day to the next, I saw about 26% of the traceroutes changed. So we're sometimes missing a few hops, but it seems like we're doing pretty well. And the differences seem to largely be either because we can't identify which IPs are actually on the same router, and also because path changes or load balancing are slightly distorting the correct path. And this is even considering those cases when we have to assume a couple hops of symmetry. There might be some other reasons why there would be differences between what we'd see and what Traceroute would see. For instance, there's hidden routers. About 16% of IP addresses turn up in RecordRoute, but not in Traceroute. A similar percentage turn up in Traceroute, but not RecordRoute. There might be instances when our destination-based assumption doesn't hold. For instance, if we probe into the middle of a tunnel, we might see weird routing. And I'm not aware of any cases, but maybe some of you will be able to tell me that there's instances when packets with options enabled are handled differently than other packets. So I've shown that our technique works pretty often, and it can give you very similar values to if you actually could measure a traceroute from the destination. And now I'm going to walk through an example of using it. And this is motivated by that original example in the beginning when the content provider wants to be able to debug performance problems. So here, I had a node in Orlando from Planet Lab that measured a round-trip time of about 150 milliseconds to an address in Seattle, and that's 2 or 3 times what you might expect. So with current practices, you might issue a trace route towards the destination and check and see if it's indirect. So that's what I did to start. And hopefully you can see the trace route starts in Florida, it goes up to DC, and then it comes back down to Florida before continuing across the country to Washington. So that big detour up through DC wastes about 50 milliseconds, and that explains some of the latency inflation that we see. But it doesn't explain this big jump between the 9th and 10th hop from 53 milliseconds to 149 milliseconds. So with traditional tools, we'd really only have a partial explanation of what's going on. If you look at the 5th hop, you'll see there's also an inflated latency of 116 milliseconds. That might also be another bad reverse path. But in this case, because that doesn't carry through onto the 6th hop and later on, it's not affecting the round-trip time that we're seeing. So with our tool, you can supplement that trace route with a reverse trace route and look for indirection along the reverse path. So that's what I did. Issued the reverse trace route, and we see that it starts in Seattle, goes down to LA, comes back up to Seattle, and then proceeds across the country through Chicago and Virginia. So there's this big detour down through LA, and that does explain the rest of the latency inflation that we saw. If you look closer, you'll see that what's happening is it's going down to LA on Internap. It's switching over to transit rail in LA, and then coming back up on transit rail to Seattle before continuing across the country. So this is not necessarily a problem. It might be the case that Internap and transit rail actually only peer in LA, and so it has to go down there. But we were able to verify with a trace route from University of Washington, in fact, they peer in Seattle as well. And so maybe it's some out-of-date information that's going on. And I actually talked to operators from those ISPs and verified that this was an unintentionally inflated path. Without our tool, there's really no way to understand what's going on or who you might want to contact to fix it. To summarize, I think Traceroute's a really useful tool. I use it all the time in research. I'm sure many of you use it operationally and for troubleshooting. But it doesn't provide the reverse path. Our reverse traceroute technique sort of fixes this limitation and provides complementary information to what you get with Traceroute. We saw that it's able to give you most of the same hops that you would see if you're able to issue a traceroute from the destination, but without requiring you to control that destination. I think it's really useful for troubleshooting, and I think it also could give you more of a complete picture during unreachability. I'm not going to get into our ideas on that now, but if you look at the slides that are online, there's some extra slides at the end of the talk that show my ideas for that, and I'd be happy to talk to people about them. I've presented a technique that we think could be very useful, and we really want people to use it. So I'd like to conclude by briefly talking about that. We're building a downloadable tool. We're doing internal testing right now. In June, we plan to put up a website that will let you use our reverse traceroute tool to measure the path back from any destination to our sources. Once we've tested that a bit, we're going to go public with a full downloadable tool in July that will allow you to use our reverse traceroute system and distributed vantage points to measure paths back to your sources from any destinations that you care about. You can email me, ethan@cs.washington.edu, or talk to me while I'm here if you'd like to be an early user of that. We'd love to have people helping us out with it, and we'd love you to be able to use it in your work. Also, the coverage of the system is tied to the distribution of vantage points that we have. And so we'd like for people to, we'd love if anyone wanted to host a vantage point for us. It would be similar to hosting a public traceroute server. Equivalent load, equivalent security. There's going to be admission control on it because we're going to be the only ones who are talking to it. And that will help everyone get better paths. So if you're willing to host one, we're developing code right now that's going to ensure safe rate limiting, spoofing safety, admission control. And again, please contact me if you're interested in doing that. Thanks, and I'd love to take any questions or ideas that you might have about this or applications for what we should be looking at.
Thank you very much. Are there any questions for Ethan right now? Bill?
So did you separate out your success rate on number of hops versus success rate on correctly identifying hops?
So are you saying, is the reason that we don't do well in some cases because we're not identifying all the hops?
Or you're identifying too many hops and trying to identify hops that don't exist or whatever?
I say putting in extra hops. So the one part of that that I looked at is the first graph that I presented was how many hops do we have to assume that we can't directly measure. And if you just look at the paths where we don't have to assume any, or we have to only assume one, then we do better than that 87%. I think we get 93% of the same hops that you've seen with Traceroute. I haven't looked much at this question of whether we're inferring extra hops in the middle. You end up seeing that sometimes when you're using record route anyway, even if you're just measuring a forward path, just because about 16% of routers are going to respond to record route that don't respond to traceroute. But I haven't looked specifically at how many extra ones.
Shane.
Hi, Shane Kerr, ISC. You documented some of the limitations of the protocols. I remember quite a few years ago someone had the idea to actually introduce a trace route that records the full route as an ICMPv6 option. Mm-hmm. Have you done any protocol design or documented what you would like to see so that you don't have to do this right. kind of heavy-handed way of getting a reverse trace route?
Right. I haven't specifically looked at that. I know that a number of people have with IPMP and okay. There was a proposal for V6 record route, but that's not something that I've specifically looked at.
Oh, okay.
If I understand how the tool works, it seems it can be used also for a quite interesting survey, which is the deployment of BCP38. You said that in practice, it's very, well, you can spoof IP address most of the time. You didn't meet a lot of ISP where it was prevented, filtered out? So from Planet Lab, about 20% of the Planet Lab nodes, there's a couple hundred that we tried, about 20% were able to spoof. I haven't looked specifically at that, but the MIT Spoofer project is looking at that. And
they found pretty similar results. About 20% across the internet that they were able to test were able to spoof. There was a discussion on Nanog. It was probably August or September that was prompted actually by a preliminary version of this work that I gave. And there was some discussion. Some operators thought that the 20% was actually very low. There didn't seem to be too many people who thought it was high. But yeah, check out the MIT Spoofer project if you want more information about who's filtering and how much filtering.
One more question.
Volodymyr Yakovenko, Google. I'm just curious, in forwarding past Traceroute, you often reaching ECMP nodes, and it's kind of difficult to process this data. And on return path analysis, you should also be hitting ECMP inside given network. How are you identifying parallel paths? And what's your observation on number of parallel paths you may encounter from source A to source B?
Right. I haven't done, I would say that this was a preliminary study, and so I've seen that we are measuring parallel paths. I haven't looked that much at how many we're seeing. I think that a promising addition to this work, that's something that I want to look at, is since we are using multiple vantage points anyway, we can make redundant probes and try to measure the possibilities and also try to use that to identify other weirdnesses that are going on. If we see different routing from one vantage point versus another, that might be cases where our destination-based assumptions breaking down. You certainly, if you look at the probe data, you do see the parallel paths, but I haven't assessed it in detail yet.
So I would just suggest you to collect some statistics because apparently the number of parallel paths which you encounter in contemporary internet is quite high.
Yeah, it certainly is. I think that the ability to measure any path that might be the right one is a good step. And generally, even if you are seeing parallel paths, they're going to be, they might not be the one that a particular data packet traversed, but they're going to give you a good idea of what's going on.
Yep. Thank you.
Thanks.
Thank you very much, Ethan. Okay, this was the